Okay, welcome back. Yes, we have now reached the point where we are going to ask the eigenvalue question. Before I get to eigenvalue question, let me tell you that the word eigenvalue is a German word. In English, it means characteristic value. Characteristic. So there are certain values that are characteristic of the tensors, that are intrinsic with the tensor. Before I tell you what is intrinsic with tensor, let me tell you what is not intrinsic with a tensor. The components of a tensor are not intrinsic because those components vary with your coordinate system. If you define another coordinate system, you get new components. Just like if you refer a vector to a set of coordinates, if after that you now invert those coordinates, what we are saying is that there are values. The values of your coordinates, of your components, are not intrinsic. They can change if you just change the basis of reference. But there are these, but you know that whether you change your reference or you don't change your reference, the magnitude of that vector will not change. So that magnitude is intrinsic with that vector. So also there are things that are intrinsic to a tensor, and they are called eigenvalues. And when they are directions, they are called eigenvectors or eigendirections. Or if you translate them strictly to English, they should be called characteristic values and characteristic directions. But in the science, the word eigenvalue has stuck. So that's what everybody says. But remember what it means. It's a characteristic value. Now, what we want to do in this place is this. Suppose we have a tensor. Let us say the green line there is, so let us say the green line there is a vector. And you know that a vector can be transformed by a tensor. Imagine a situation where what the tensor does is that it changes the magnitude, but it does not change its direction. It's either directly there or directly opposite. Is either a scalar multiple or a reduction or anything. Then what happened? Is it possible? If it happens, what can we say about it? That is the eigenvalue question. I will pose the question a little bit better now. Before I do it, let us compare vectors and tensors. Let's just compare the two. Now, the one in the column of vectors are things you know very well. And the one on the right column, the middle column, are things you know very well. On the one on the right column are the tensor equivalencies that we have now learned. So what happens is that anytime you forget the way a tensor should behave, go back to the vectors you know very well, and you can extrapolate and you say, oh, okay, this is what will happen. When you talk of Cartesian basis, of course, in vectors there are three bases, E1, E2, and E3, which you used to call Ij and K. But for tensors, there are 9 bases, which is E1 diad E1, E1 diad E2, E1 diad E3, E2 diad E1, E2 diad E2, E2 diad E3, E3 diad E1, E3 diad E2, and E3 diad E3. I am not in a hurry. I said all the 9 because those are the only things. So whereas you can resolve a vector into 3 bases, you must resolve a tensor into 9 bases. But after that, the resolution is the same because of the resolving. So you can write your vector as v1 e1 plus v2 e2 plus v3 e3, and using the summation convention, we can write it like this. Similarly, you can write your tensors as t11 e1 e1, t12 e1 e2, t13 e1 e3, t21 e2 e1, t22 e2 e2, t23 e2 e3, T31 E3 E1, T32 E2 E3, and T33 E3 E3. That is, but our summation convention helps us to write that thing in so simple a form that after some time we can see we are trained enough that we can see 9 things, 9 sums here, where we see 3 sums here. So that is it, because you can see the power of our summation convention. It makes the way we write the vectors and the way we write the test almost equally simple. But you do not forget that there are three. This is a pack of 3 things, whereas this is a pack of 9 things. Let us say, okay, how do you evaluate the component of a vector? If I give you a vector and I give you E1, E2, and E3, how do you find the first component? You just take the inner product, the scalar product of the vector with each of the bases. If you take the inner product of the vector with the base 1, you get the first one. If you take it with the base 2, you get the second one. If you take it with base 3, you get the third one. Similarly, you want to get your 9 components. You just take the scalar product of the vector with the 9 bases. You take it with E1, E1, you get T11. You take it with E1, E2, you get T12, and so on. That's how you do it. You can write it like this. It is exactly the same thing as writing it like this. If you doubt it, go back to the set of, you will see that this and this are exactly equal. Here, it is just something like this. You can see that instead of taking the vector scalar product with the vector base, you are now taking the tensor scalar product with the tensor base. That's all. So you can see that if you forgot this, remember this, and to help you to extrapolate back to this. Now, if you want the magnitude of a vector, how do you do it? You take the square root of the scalar product of the vector with itself. Or if you want the magnitude of a tensor, then take the magnitude of the scalar product of the tensor with itself. Finish. It's the same thing. Remember, the magnitude of a tensor is not the determinant. The determinant is another definition. The determinant is the trace of a sum. It's the trace of 3 things. That is the trace of the magnitude is where there is a way you take the determinant is a fraction, which we defined as the trace of the transpose when you say TU, TV, TW divided by TU, VW in scalar triple products. That's what gives you the. So the definition of determinant is different from the definition of magnitude. So do not, even though both things give you scalars, but they are not the same scalars necessarily. It might there will be situations where they be equal, but there is no, that's there is not important. Now, when you say scalar product, there is a scalar product which you already know very well. The scalar product of tensor is this one. There is also defined in certain textbook a scalar product different from this, which is this one. And should I let me take some time off and define this one for you so that you will know that it is easily defined. Let us go back to where the other one is defined, and then we'll see how did we define the one scalar product so that we can define the other one for you. Because if you read widely, you will see some textbooks that spend time to define another scalar product. Okay, it's around here. Okay, now the one with the 2 dots in a column is defined this way. The one with the 2 dots in horizontally is if you do not put this trace. If you just say trace of ST or trace of without any transposition of either one of them, that's how you get the one in the. So let me write it here so that you will see it. So I can say copy. I want you to be careful to see it. How do I do this now? This brackets, where are the brackets? Where are my brackets? Where are my brackets? Yes, these are my brackets. Okay. So what I'm saying here is that you can see C dot C dot. Okay. It will be trace of S alone. And T alone. Okay, so these are two different scalar products. So you can do, if you do this, one of them must be transposed. If you do this, neither of them is transposed. And so some textbooks define this scalar product, some other textbooks define this scalar product, and some define both. But the first one is the one we will use. But this one exists too. So you can, and it is a proper scalar product too. It will give you a scalar value. So those are the two scalar products that you can get. So let me go back to the one we are looking at, which is slideshow from the current thing. So we can have this or this. So you can see when it comes to tensor, there are usually variety of different things you can do. So here, only one way of doing a scalar product. Here, there are two ways of doing scalar product, but this is the one we will use in this course. Orthogonality. You say two vectors are equal if the scalar product is 0. And there is a geometrical interpretation of that. They cross each other at 90 degrees. Here, two tensors are also orthogonal if the scalar product, either this one or this one, if the scalar product is 0. If their scalar product is 0, you say they are orthogonal. Unlike the vector case, this one does not have a geometrical interpretation, but it has an algebraic interpretation. Very often, whenever something has both a geometric interpretation and also an algebraic interpretation, the algebraic interpretation goes far, far beyond the geometrical interpretation. The geometrical interpretation only goes some distance, but you can make much more conclusions. You can get much more things done with the algebraic interpretation. So whenever you have both, just stick to the algebraic interpretation after you have been helped to agree with the geometric interpretation. Now, what about zero element? Of course, there is a zero vector. A vector can have a magnitude of 0, so that's a zero vector. In the tensor, there is the annihilator tensor that's equivalent of that. That is zero vector. There is also can be a unit vector. I didn't do that. Unit vector. Oh, what would be the tensor equivalent of a unit vector? Go back to the chat room, and I want to try you. I want to be sure you are awake. If there is if we want to get an analog for the unit, you know what unit vectors are. What would be the analog for the tensor that will be equivalent to the unit vector? So go to the chat room and let me meet you there, and you tell me what you think we should have for the unit, for the equivalent of the unit. So, okay, I see Ademola. I've seen you. So anybody else? Ideas? Is anybody else awake in the class? Let me see who else is awake. Okay, Daniel is awake. Anybody else? Wake up, wake up, wake up. I want 2 more before I move on. So, class, wake up. Okay, okay. Okay, good. So you can see we have perfect analogs. Virtually anything you see in vector analysis has an equivalence in tensor analysis. So slideshow from current slide again. Okay, so what are we saying? What we are saying is that if you forget any of the things we have done, you can remember them by remembering the things you already know in vectors, and you know there is an analog. And once you just do the correct analogy, that thing will come back. So your vectors help your tensors. If you are poor in vectors, it is not possible for you to know tensors. But if you know vectors very well, it is easy for you to become very good with tensors. The last thing, when we talk of products, we can talk of multiplication by scalar, which you know, which is a scaling. We scale the vector. Or we take scalar product between two vectors. or we take the vector product, the scalar product between two vectors will give us a scalar result. The vector product between two vectors will give us a vector result. The tensor product will give us a dyad, which is a tensor. So one gives us, this one gives us a vector, this one gives us a scalar, this one gives us a vector, and this one gives us a product. So you can see that when between two vectors, when you are talking about products, there are several ways you can do it. And that is why we use signs to tell us which one we mean. If you just put two vectors together and you say you are taking a product, you have not given us enough information, because you have to disambiguate so that we will know which one of this you are talking about. Similarly, with tensors, you can also scale. You can multiply it by scalar, which gives you a tensor. You can operate a tensor on a vector, and the answer of that is a vector, because if you operate a tensor on a vector, it gives you a vector. You can also do composition. You can operate a tensor on another tensor, which is a composition. If you use a composition to operate on a vector, which one do you operate first? Is it the one on the left or the one on the right? If you are using a composition to operate on a vector, please see me in the chat room. If you are using it, I will put the question in writing so that you can answer it, because that question is very important. If a composition, say ST, operates on a vector U, so that you have ST operating on U, which tensor operation comes first? Which tensor operator comes first? Is it S that comes first or T? Do you do S first and do T, or do you do T first and do S? What today? So T first, and then after that, what do you do? After T, what do you do? Yes, what do you do? And then that is great. Aishat, you are fantastic. You see, you now operate S on the result of TU. You are not just going to operate S on U. You see, you operate T on U, and then you operate S on the result of TU. When you do that, you have done the composition. That is what it means to operate a composition. You do the one on the right first. You know, it is not the one on the left. You start from the right. You do the one on the right first, then you do the one on the left. So that means that STU is different from TUS, TSU. TSU means you operate S first, and then you operate T on the. So the ST is not necessarily the same thing as TS. It's not. It's not the same. It's not necessarily the same. It may be, but it may not be. So, but there's nothing that guarantees it should be. So that is good. So Aishat, very good. Okay, so we said we can multiply by a scalar. We can do operation on a vector. We can do a composition, and we've already explained what composition means. Then we can do scalar products. We already saw that we can define up to 2 different scalar products, and then we have several tensor products. For this class, we will not go into tensor products of tensors. We only talk of tensor products of vectors. If you now have something like this, let me write it here. Let me write it here so that you see how it looks. Okay. If you have something like this, that is a tensor product of S and T. This is a big complicated object, and our ability in this class does not reach for us to be discussing this. But just know that just like you can have this sign operating between 2 vectors, it can also happen between 2. It can also happen between 2 vectors. You can even have S dyad V. This kind of product is also possible. Apart from the one we have talked about, this type of thing is possible. But again, we are not discussing this in this class. So let me just remove that so that it's not, because it's not a scalar product. It is a tensor product. It's possible to have tensor products between two. It's possible to have tensor products between two vectors and between two tensors. And there are several results we can prove. But we are limiting ourselves right now to multiplication by scalar, operation on a vector, composition, and scalar products. We will leave this one for now. Once you master this, it is easy to introduce some of these things when we need them. Right now, we don't need those. Okay, so what I've said on this slide too is that there are several things you can do by analogy with vector analysis. And if you forget what you were supposed to get, you can use your knowledge of vector analysis to your advantage. And if you know what to do, it is possible for you to remember what you might have forgotten in tensor analysis. Now, I pose the eigenvalue question. The eigenvalue question is posed like this. We received formulas for computing principal invariance and took these formulas as definition of principal invariance. These formulas arise from deeper analysis. And I think maybe 2 lectures from now, I'm going to now show you the practical things that you will need this knowledge to be able to do. If you don't have this knowledge, you are short of these practical things. And there are things about design, especially when you are using modern products like Fusion 360 and modern computer things to design. Many people go into all the simulation that they think they know what they are doing. If you don't know tensor analysis, I will show you things that you will be seeing there that you think you know, but you don't know. That will now your eyes will now be open to them. I will do that 2 lectures down the road because some people are already not very happy because they cannot see these things look so theoretical. They cannot see why are we doing this. I will show you why, and because after you have learned why, you will be able to continue. By the way, the books you are using in this class, in about 3 months' time, they will be available. They will be available in print form. So if you want to continue, you can continue your learning. So we already have materials on the we already have materials on the web. You can be tested. You can be testing yourself, and you can also look at the videos we have done virtually on all the chapters. So you can learn on your own, and then I will show you where that knowledge will take you. So these formulas arrive from deeper analysis. Those deeper analysis will be shown you when you get the books in print form. The books are available to you free in what do you call it, in PDF form. So we already saw that the cofactor transforms area vectors. That is, if you want to compare the area transformed by a tensor in the length, you need the cofactor. We also show you that the determinant relates the transform volume to the original volume. We will ask this question from the standpoint of tensors and show how it leads to several important results and greatly assist the engineer in solutions that may not have been possible otherwise. Determinant and transformation of volumes. For instance, look at the parallelepiped formed by UV and W. If T transforms that to TU, TV, and TW, if UV and W are linearly independent, the original volume UVW cannot vanish. That is actually the definition of linear independence. If UV and W are linearly independent, that means that UV and W, the volume is not trivial. If T is invertible, if T is not singular, neither can the transform volume vanish. And there is a question in question 226, which shows that the transform volume cannot vanish. Just the way the transformed, the original volume cannot vanish. If T is invertible, question 226 proves that the volume transform can also not vanish. So neither of them can vanish. And the volume of each case is a scalar. So we can take the ratio of the two because the ratio of the two are 2 scalars. One is the volume of the transform, the other one is volume of the original. If you do that division, you get the determinant. In mathematics, you will tell the mathematician will tell you the meaning of determinant. For the engineering point of view, this is the practical meaning of determinant. The determinant has practical usefulness. It's not just theory. It is what tells you. Now, this change in volume could be caused by heat. If you heat, you know from your physics that if you hit an object, it will expand. You talk of coefficient of linear expansion, coefficient of surface expansion, coefficient of cubical expansion. By how much? An engineer is not just interested in the fact that the thing has increased. He wants to know by how much. Why? Because if you are making a thermocouple, if you are making something to like a sensor to turn off the heat, you may use the length to turn it off. You may use the volume expansion to turn it off. So that has a practical usage. So you are not just saying, oh, the thing has increased in volume. You want to calculate by how much. So to calculate by how much, you need to calculate the cofactor. If it is volume, you need to calculate the determinant. So which are the scalar invariants of the tensor? All these things are characteristic values. They are deep intrinsic values of the tensor. So you see determinant and transformation of volumes. Let us move on. Now, what is the eigenvalue question? A tensor linearly transforms one vector to another. When we use a tensor to transform a vector to another vector, we cannot always predict the outcome of a tensor transformation other than the fact that we know that it must be a vector and that the transformation is linear. If we know that transforming a tensor is a special, if we know that the transforming tensor is a special tensor, such as an identity. For instance, if I tell you to use identity to transform a vector, you already know the answer, don't you? You already know the answer. If you know that the tensor I gave you is an annihilator, you already know the answer. And let me just be sure that you know the answer. Let me go to the chat room because I can't see your faces, so I don't know whether you are agreeing with me or not. So I want to go to the chat room. I want to tell me when we use, okay, if I use an identity to transform U, what do I get? If I use an identity to transform U, what do I get? Aishat is always coming first. Aishat said it's an identity, the same vector. Identity. Okay. In fact, Daniel Sadiq has gone further. He's already told me what I will get. If I use an annihilator, I will get a zero vector. Let somebody tell me what I will get if I use a spherical tensor. If I use a spherical tensor, what do I get? What do I get? If I use it, suppose I have gamma, let me just, suppose I have AI, where A is a scalar and I is an identity. What do I get if I use the spherical tensor AI to transform U? So AI, where A is a scalar and I is the identity tensor. So I'm just scaling the identity, which means that you have a tensor that have A and the diagonal and zero everywhere else. If I use that to transform U, what do I get? Okay. Let me give you as an objective. Is it A cube U or A U? Am I going to get A cube U or A U? Let's see. Remember that U is a vector and not its component. U is the vector, and A is the scalar. And what is AZU? What is the meaning of AZU? I don't know what is. Yes. Okay, Daniel is right. Daniel says it's AU. AU, yes. It's not A cube U, but just AU. Good. So if it is the if it's the annihilator, what do I get? I get zero. I get zero vector. Which other vector do we know? Which other vector do we know? We've talked about the identity. We've talked about the spherical. We've talked about the annihilator. What other vector do we know that's a special vector? Identity, annihilator. Okay, we can go back now. So like this, I'm sure I can see that you are following. Let me remove this. I'm not feeling hot. I was feeling cold before. Okay, so let us go back to the slideshow. So we can say we know that transforming is if the transforming tensor is a special tensor, such as an identity, a spherical, or an annihilator, or a rotation. If it's a rotation, we know that U will be a rotated form of U without changing its magnitude. It's only direction that will change. We know that. So when we have additional information, we can predict the outcome of what the vector will look like. But if we do not have any information, I just give you a tensor. I say, I'm using this tensor to transform this vector. You cannot know anything about what type of outcome I will get. You can't. So we now suppose I just have a general tensor. I have not told you its identity. I've not told you its annihilator. I've not told you its spherical. I've not told you its proper orthogonal. I've not told you its rotation. I've not told you its reflection. I've not told you anything about it. I just said I have this tensor, and it suddenly happens that when I operated it on you, the result that I got is just a magnitude change. It didn't change anything else. And it's not a spherical tensor, it's not an identity tensor, it's not any special tensor. It's just an arbitrary tensor. When I put other vectors, it gives me normal result. But for a particular vector, it just gives this type of result. That is the eigenvalue question. Suppose we have, for a tensor we do not know to be any of the above special tensors, a situation such that Tu is equal to lambda u. It does this not to all vectors, but to particular ones for particular scalars. The transform vector is simply a scalar multiple of the input. Of course, you know that if it's just a scalar we use to multiply u, that result is not unexpected. But remember, here, it is a tensor we used. And the result we are getting is the result we should have expected only from a special tensor or from a scalar multiplication. When that happens, and it happens, it turns out that it happens. I can give you 20 examples that you will do it, and you will see that if I give you lambda and u, that when you do it to a particular vector, what you will get is when you operate the t on u, you are just going to get a scalar multiplied by u. That's all, nothing else. What we are asking is, if this happens, what can we say about lambda and u? The question, not what is happening here. The tensor is actually pretending to be a scalar, or at least pretending to be a spherical tensor, when it is not. Remember, this particular tensor is not a spherical tensor. In fact, it has the whole 9 components populated. It's not just having elements only on the diagonal. It has elements everywhere. And its behavior is pretending that it is a spherical tensor, is pretending it is a scalar. Several questions arise. Why does this happen? Why? Why does this strange behavior? That is the eigenvalue question. Is there any relationship between the tensor and the vector that produces this special location? Is there any relationship? Because it doesn't do it. This thing is doing, it doesn't do it for all tensors. It just does it for about 2 or 3. Every other tensor, it behaves as if it's normal. But if you bring some specific vectors, it just changes its behavior. It starts pretending as if it is a scalar, or as if it is a spherical tensor, when it is not. You know it is not. You know it is fully populated. Now, what about the lambda? The lambda you saw there, this lambda that it has, is this lambda and this u, are these two things, and do they have any special relationship? Is there any relationship between them and the tensor? What if the scalar multiplier is unity? If that scalar multiplier, in this case, in case where the scalar multiplier is unity, you operate a tensor on u, and what you get back is u, when the tensor itself is not an identity tensor. You know that ordinarily, if it's an identity tensor, you will know that when you operate it, it will give you u. But it gives you u, and it is not an identity. You know it's not an identity tensor. You know what an identity tensor looks like. An identity tensor has 1, 1, 1 on the diagonal, or delta ij on all its components. That is the question we are trying to. That question is the most important question you can ask about tensors. The question we have just finished. The answer to this is what tensors are all about. In fact, all the usefulness of tensor is about this behavior. That is why I wasn't rushing into it. I wanted to be sure you have reviewed, you understood the other things, because all the other things are needed to understand where we are now. You are now standing on a higher ground. By the time you can answer this question, you really know what you are talking about when you are talking about tensors. The eigenvalue is the characteristic value. Vectors that satisfy this equation we have been looking at are called eigenvectors or characteristic vectors. Their corresponding scalars are called eigenvalues. Once you know the eigenvalues of a tensor, you know the principal invariance. You know the principal invariance in a form much simpler than the equations we were looking at last week. In fact, you know virtually everything you may want to know about the tensor. Once you can find the eigenvalues of a tensor, there are only 3 of them. If you know those 3, you don't need to worry about all the 9 components, the dyads, and all those things, because what is important about the tensor is known to you. So let me backtrack a little. What we are saying is that if I give you a tensor T, and you can find U, a general tensor T, not an identity tensor, not an orthogonal tensor, not a rotation tensor, not an annihilator tensor, not a spheric, none of those ones, just a general tensor. And you can find U and lambda that will make this equation true. The U here is an eigenvector, and the lambda here is an eigenvalue of this tensor. They are character properties of this tensor. They are not just arbitrary. They are related. They are the children. This lambda and the U are like the children of this tensor. They are intrinsically part of this tensor. And they are called the eigenvalues and the eigenvectors. Eigenvalues and eigenvectors are often the quantities engineers seek in a typical tensor. If an engineer is faced with a tensor, it can be the stress tensor, which determines the stresses in a material body subject to loads. The engineer is looking for the eigenvalues and the eigenvectors. The physical interpretation is wide and diverse. From material science, where the eigenvalues represent the principal stresses, and the eigenvectors represent the principal surfaces or principal directions, to dynamics, where they are the natural frequencies and the mode shapes, to electrical circuits, where they are also where they govern resonance and several other applications. In fact, this problem is so much applicable to virtually every engineering discipline that the mathematicians are the people that have the final word about it. It's taken away as if it's a mathematical issue, because also the mathematicians have formulated the theory deeply, because it is the same thing whether you are dealing with a civil engineer or a mechanical engineer or an electrical engineer or any engineer. They always have to deal with the eigenvalue problem. In fact, that is the reason why you study tensor analysis, because of the eigenvalue problem. Before we move on, let us look at a normal tensor transformation. If you begin with vector V1, let us transform it with the tensor transformation TV1, where the tensor is T. If we have broken the tensor into its 9 components, we can write it in the form here, E1, E2, E3, circle times 3, 4, minus 2, 1, 4, minus 2, and so on. And we can now do TV1 is equal to this. We can do it. It's a little bit it's a little bit tedious arithmetic. You can do it like this. You can see that the ones that will produce E1 are the ones that the first where the first diode is E1. That is the one that will produce this along E1. Where the first diode is E2, that's the one that will produce this along E2. Where the first diode is C3, that's the one that will produce. So you can do this, and you see that it will become 1E1 minus 2E2 minus 3E3. And this is just ordinary transformation. Or you could just come and take the matrix of the tensor. If you take the matrix of the tensor and you take the matrix of the vector and you multiply them, you get the same thing. So you can turn it into a matrix analysis and you get the same answer. Whether you use the tensor transformation or because that is why mathematicians use a word. The word is equipolency. Let me just type it somewhere. I want to type the, did I? Okay, it's in the next slide, so I didn't miss it out. So we can calculate the eigenvectors of the tensor using its matrix representation. Here, there is an equipolency between matrix theory and tensor theory. So equipolency, it looks like a big word, but it's not. Let me just tell you what it means. It means that they have the same force. What you are doing in matrices and what you are doing in tensor happen to be exactly the same thing, even though you are ascribing a geometrical meaning to what is happening in tensor and you are ascribing an algebraic meaning to what is happening in matrices, but the two of them are the same working, the same mathematics you are doing in both cases. So if you know one, you already know the other. When that happens in mathematics, you say there's an equipolency between the matrix theory and tensor theory. That is why somebody who already knows matrices already has some knowledge of tensor theory. The mistake he can make is that it now says, because of the equipolency that the two are the same, the two are not the same. The tensor theory is a geometric construct. Matrix theory is an algebraic construct. You can see that when we are defining determinants, we have a geometric meaning. When we are defining cofactor, we have a geometric meaning. When we are talking of a vector, a tensor operating on a vector, we have a geometric physical meaning. All those, the reason why we are studying tensor theory is not to just play with some matrices and some algebra, because we have use for them. That can help you design something that can cut a current by expansion, because you have calculated what the expansion will be, and you have calculated what the area expansion will be, you have calculated what the volume expansion will be, and you can use it for something practical. It is useful for computation, but they are not the same. Like now, let us look here. In this expression, the expression on slide 10, you can see there's a matrix there. There's a matrix there, but that matrix is not the tensor. The tensor is the dyad of this on this. The matrix gives you the essential of the things contained here, because what is left are the coordinate systems, the coordinate unit vectors that are left. But the coordinate unit vectors is what makes this thing a tensor. This is a matrix. You can see that every tensor has a matrix, but not every matrix has a tensor. You can put numbers together and you have a matrix and you can go and do all your math. But this is a tensor and it's different. So you need to tell yourself, you need to know for yourself the difference. This is one way of showing you the difference between a tensor and a matrix. So, such that you also know there's a difference between a vector and a matrix. This is a matrix. But if it's a tensor, you have E1 minus E2 minus E3. So it is related to the coordinate system. So that is why it is a vector. But in normal literature, especially when you go to artificial intelligence, this matrix here will be called a vector. But that is not correct. It is a matrix. It's a one-dimensional matrix. If it becomes a vector, it has to have some vector basis associated with it. But you need to get used to it, because textbooks use it carelessly and they talk carelessly about it. And they say, oh, this is a vector and this is a tensor. And in fact, when you talk of tensor flow and pie chart, and the other one in that Facebook people did. What is it now? It's PyTorch. PyTorch. All those things, they mix the terminologies a lot, but you need to know that seriously there's a difference between the vectors and the matrices. You can also use Mathematica. You can use Mathematica to do the multiplication. You can also use to calculate the eigenvalues. For instance, the eigenvalues and the eigenvectors of this particular vector that is there on the right-hand side are given. If you type into Mathematica, Mathematica will give you the 3 eigenvalues, and it will give you you can also get the eigenvectors from there if you want. Eigenvectors and eigenvalues can be given to you. Now, transform an eigenvector. So if you now take a vector that is an eigenvector of the tensor, and you try to transform it, what do you get? Note that for the tensor we defined, is 3 eigenvalues, E1, E2 plus 2E3, E2 plus 2E3, and E1, E3. Now try to transform any of these vectors using T. Magic happens. There will be no rotation, only an elongation or a reduction in size. This amount of elongation, the scalar multiple, is the corresponding eigenvalues. Now, as an example, the graphic here is the transformation of E2 and 2E2. So the vector in the red is the result of using E2, and so you can see the vector transforming and the vector transform 2 are exactly along the same direction. So you can try those out. So we have explained the eigenvalue question. What is left from this set of slides is to now be using calculations to now calculate how do we get, if you give me a tensor, how can I get the eigenvalue? What is the theory behind it? And how can I express the principal invariance in terms of the eigenvalues? How can, suppose, since the eigenvectors are vectors, what is the relationship between them? You'll be surprised that the eigenvectors of a symmetric matrix are at right angles to each other. So they can form a coordinate system. And if you use so that means that you can now refer to the eigenvalues in terms of their coordinate system and get an eigenbasis, because you can get a basis for the vector, for the tensor, using its own eigenvalues. So you know that whenever you get a basis for a tensor, you say you have a basis. You can have 3 vectors, and you say these three vectors, because they are linearly dependent, and you can express any other thing in terms of them. That's a basis. But what if the basis you have is actually what you calculated from the eigenvectors of this particular tensor, and you are now expressing the tensor in terms of them? Then they are not ordinary bases, they are eigenbases. So you see, we talk of eigenvalues, we talk of eigenvectors, and we talk of eigenbases. Now, if you start this example here, you see T minus lambda U is the same thing as T minus lambda I operating on U, because you cannot just say T minus lambda, because if you say T minus lambda, you are subtracting a scalar from a tensor, which is not possible. You first of all have to convert this one to a tensor. So T minus lambda I is a spherical tensor made from identity and lambda. So if T minus lambda I is operating on U, so here you can write these ones in terms of their components. T, I, J, E, I, diag E, J is T here, and U is U, K, E, K. And lambda U, I, E, I is this one operating, because the lambda U, I, E, I is the spherical tensor operating on this. If you write them like this, and you open this bracket, you have delta JK here. If you do that and open it up again, you have this, and then you have Tij minus lambda delta Ij into Ujei is equal to the 0 vector. So this is the stating the eigenvalue question in terms of mathematics. So if you write it this way, again, just confirm to me that every line here, the equality on every line is clear to you. I can see that I have only 3 minutes to go. What I want to do, I knew that I would not be able to finish today's slides. So what I want to do is to stop here. I would send the slides to you. I want you to read the slides through so that by the time we meet again in the next lecture, it will be easy for you. And on slide 15, make sure you can account for 1, 2, 3, 4. There are 6 equalities on this. We are saying that please account for all the 6 equalities there. How do you get from one to the other? Just make sure that you understand that in full. And then I will send the slides to you, and the same slides we are using now, we are going to use it next week. I will start again from the beginning, rush through the first 15 slides since we've already gone through it. But I expect you to go through the rest of the slides and answer the eigenvalue question. Once you finish that, and we have the next thing is that I will try and show you, before we move on, I will try and show you how this applies to you as an engineer. Where do these things play out? And you will see that it is so fundamental to the duty of an engineer to know this much. If you don't know this much, I will show you the things that you cannot learn because you don't know them. So have a nice day. We'll see you again next week. And before then, your slides will be ready with you. Bye.